I will present today is an ensemble-based method that I developed like a year ago. And this method is mainly about unsupervised learning. So we use cluster-based analysis to detect anomalies from the data, but it's not like a normal clustering-based algorithm, it's an ensemble-based algorithm. So how many techniques you will develop to detect outliers in a cooperative fashion, this is the big question. So before I take you to the model, I would like to share with you what is clustering is. Clustering is an unsupervised learning process. Give me the data, I would try to find the similarities and dissimilarity in the data, and I'll find those hidden groups, those hidden structure in the data, such that objects in the same cluster are similar to each other, meaning that the distance between objects in the cluster are minimized, and the distance between objects in different clusters is maximized. How many cluster techniques have been seen in the market of computer science unsupervised learning technique? Many. All of them works well? They might. They might work well in this data set. They might underperform in another data set. So we said, let's try to develop a model that is working in a cooperative fashion. I will ask technique A and technique B, technique C, technique D, technique 100 to involve and cluster the data. So I'm going to look to the end results of those techniques. That's why we call it cooperative learning, because we wait until everybody finishes its clustering process, and then we take the decisions that are obtained from each individual to find a cooperative learning process to come up with a new clustering result that is better than those individual techniques. So the model starts by involving the data. Of course, we have to do some feature selections and some pre-processing offline, because if we deal with large data set, we cannot do this online all the time. So we did some feature selection, and we did calculate the similarity between every entity in our data set, and we store this in a matrix we call the Similarity Matrix. However, the similarity measure that you will use, it doesn't matter, because at the end you will convert it to a 1- or a scale 0 to 1 measure. And then we ask K clustering technique to be involved in the model. You could decide on this K based on how scalable your model is. And this is another area of research. If you're interested, you could try it later. So once we have K results, each result has, we have C results, like C technique, and each technique has K clusters. And be careful that at this stage, we assume that each technique will generate the same number of clusters. However, a more flexibility and more extension to this is to involve multiple clustering techniques with different number of clusters. And the only modification is at the stage of what we call it a membership generation process. I assumed I have asked a k-means cluster to cluster the data into 2 clusters, and then I asked the dbScan to cluster the data into 2 clusters. And then my question is, if I want to have a cooperative learning between the k-means and the dbScan, such that I started by 2 clusters, another 2 clusters from the dbScan, and then the question is, how you find a hashing function that we call a membership to find the agreement of objects based on the decision of the k-means and the dbScan together. So we started by 2, and at 2 we might end up to have 4 clusters. We might end up to have the same 2 if they agree on the same clustering process of the data, right? So if you started by by C techniques, like 3 techniques, and each one generate 4 clusters, you might end up to have 3 to the power 4 subcluster generated based on the agreement of which one belongs to which cluster. So we're gonna take those subclusters, or we call it the agreement between the clustering techniques, and we're gonna use those subclusters to detect outliers. So we use the result of the clustering method as a byproduct to detect outliers in data using clustering-based cooperative learning approach. And then let me take you to different methods that are used to find outliers in data. As a matter of fact, each method could, we call it distance-based method if it define outliers based on the distances, how far this object is from each other point in data, right? Or we could call it like density-based method. If it just say this object has a low density around it, then we assume that it's compared to every other object that is an outlier. In clustering-based, we assume that objects are outliers if they belong to small clusters. If they belong to large clusters, then why you should consider as an outlier? Is this true? What do you think? Is outliers belong to small clusters, or we could find outliers in larger clusters as well? What do you think? I need your feedback. We could find outliers in larger clusters, right? We could find outliers in larger clusters, but we say it's most likely to be an outlier if it belongs to a small cluster. So we could have potential outliers in large clusters, and we have most likely outliers if they belong to small clusters. But we will not start by the regular clusters. We're going to start by those clusters that are obtained based on the cooperative agreement among multiple clustering techniques. And then our assumption in the method is outliers could either belong to small or large clusters. Also, outliers affect on the homogeneity of clusters, because once you cluster the data and say, good, we were able to use those subclusters or those small clusters to find those outliers in data, and it turns out that you have outliers, but they have an effect on the homogeneity on the object in the clusters. So your outliers might not be good candidate to be outliers. So our assumption is if you really detect those outliers in data, they must have a bad impact on the homogeneity of object in clusters. Otherwise, we will call it a false positive outliers. So the process starts by still involving set of techniques, asking them to generate their clusters, and then we find those subclusters based on the cooperative agreement between those techniques. Instead of starting by 2 and a 2, we will have like a 4 small subclusters. And then we will assign what we call it a cooperative outlier factor. A cooperative outlier factor depends on how we define actually outliers. We define 2 types of outliers. The first one is intra-outliers, and we call an outlier as an intra-outlier if they lie in the same subcluster. However, they have far distance from all the objects in that subcluster. However, inter-outlier, we assume that they have to be in a small subcluster because we say small subclusters are most likely to be outliers. Then we assume that inter-outlier still is an object that lies in a small subcluster and it has far distance from objects in large subclusters. And then based on those definitions, I won't take you to the set of equations that we used, because if you read the paper, there are like around 10 equations we used to define the inter-outliers the inter-outliers, and also the cooperative outlier factor at the end. But keep in mind that we used histograms, we used similarity factors, we used similarity matrices, so there's many equations that you can read to find how we came up with those cooperative outlier factor that would assign a rank for each outlier. And then, this is what I meant before, is we might see outliers in small clusters, and we also might see outliers in large clusters. So our goal is to detect those outliers that might be found in different sizes of clusters. And of course, you have to determine the threshold that you will use to decide on a larger subcluster or a small subcluster. So this is another question. And then once you find those subclusters and assign a cooperative outlier factor for each object, you will return the percentage of the top ratio outliers of those data. However, the question is, how many clusters originally we requested? We started by assuming they have the same number of clusters, right? 2 clusters. But the data might not be clustered into 2. It might be better to cluster data into 3. Or it might be clustered data into 4. As clustering is an unsupervised learning process, then actually you don't know how many clusters in data. Then you cannot assume that you have to start by 2 or 3. So we had to do this on an iterative process where we start by minimum 2 clusters, and then we have a potential set of outliers. We call them potential set of outliers, like the most likely to be outliers. And then we repeat the same process at k equals 3, and we have another potential set of outliers. If we have an intersection between the 2 sets, we call them candidate outliers, and they can jump to the next level as outliers at k equals 3. And then we use those candidate outliers to be potential outliers at k equals 4. And then we repeat this until we have k equals 10, or you might stop at k equals 10, or you might keep going until you actually discover a large number of outliers that might be candidate outliers. This process is repeated based on the desired number of clusters, and this is one area that we try to enhance right now, is to know when to stop. Like you could try 2, 3, 4, up to 100 clusters, but you need to know where to stop. So we developed another measure, we call it the similarity, overall similarity measure, that the more you increase the number of cluster, the more this measure might go up or down, and the goal is for this measure is always to be increased because it depends on similarity. So as at a certain level or certain threshold, if this measure goes down, we say we have to stop here, and this is the real number of clusters in data, and this is where you will retrieve the final candidate set of outliers. And then we applied this over 23 data sets from different categories, but I'm going to show you only the results on some gene expression data sets as well as some median use data set. And we are in the current process on applying this on credit card transaction data set, because if we know that cooperative learning can find those outliers in data much better than the individual learning, then why not to apply it on different data sets? So we were able to involve mainly like 3 techniques, like the k-means and the bisecting k-means and the partitioning around medioid clustering techniques in one cooperative model. And then we use pairwise cooperation versus tribal cooperation. So we ask a k-means to cooperate with the bisecting k-means, or the k-means to cooperate with the PAM, or the 3 of them to cooperate together. And as a matter of fact, it turns out that the tribal cooperation is much better than the pairwise cooperation. So the more agreement we receive in the model, the better results we could have, because we have high confidence that those objects are together. Those objects are outliers. So how scalable this method is, we have added different version of the k-means and a different version of the bisecting k-means, and we were able to stop at 39 version of the k-means, like the 39 iterations of the k-means, and we still have good results. Afterwards, we have to stop because you don't want to end up to have a lot of singleton clusters where very, 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 very small cluster at an end result for you. And we tried, as I said before, this is over different web news. And once we have discovered those outliers, we said, let's see what will happen if we remove these objects from the data. So we removed this object from the data, and we calculated the homogeneity measure in clustering analysis. It's called like the separation index. And we would like to see the impact on removing those outliers from the data, and it turns out it has a significant impact. So our discovery process was successful. So we were able to achieve up to 56% using the cooperative learning as compared to a maximum of 44% by the k-means by itself, or the bisecting k-means by itself, and for up to 61% as compared to 40% by k-means and 34% by the PAM. And finally, using the tribal cooperation, we were able to achieve a clustering quality up to 62% as compared to the k-means, bisecting k-means, and PAM. This is for the breast cancer data set, and also up to 75% improvement in the clustering quality as compared to the 3 techniques, individual techniques, using top ratio 30% of outliers. So because currently we are working on transaction credit cards, it's a larger size data set, so we are moving our method now into a distributed version, where we apply the cooperative learning outlier detection method on each node. And we have designed 2-layer architecture network, where, like in a master-slave model, so we could detect outliers, efficiently detect outliers, and at the same time, we have less time complexity, I would say, because the more you combine techniques here, the more complex, time complexity would add to your model. So we don't want to fix this, because you don't want to sacrifice spending days and days running your technique to achieve 60%, 30% more. So we're moving this to the second phase, where we do parallel processing. So in a goal of finding better outliers in a data, and at the same time to achieve less time. And thank you. Any questions?
Thank you.